Hi there. In this video, I'm going to go over briefly an example problem in section 7.4 to show how we compute the inverse Laplace transform. And there's no real sort of great trick to doing this, or there's lots of tricks, but there's not like a formula for doing Laplace transforms. It's really just sort of using our observations about how functions get mapped to the Laplace space in the first place. We talked before spring break through a little bit of the theory of how you know an inverse Laplace transform exists and for when it does exist, what has to be true about functions in order for that to exist. And we're not going to worry about that in the video so much. You can go back and read the chapter, read your notes if you want to do that. We're just going to do some practice reading the table backwards. Basically all we've got. So I've got my table of Laplace transforms, and the theory in the chapter tells us that the Laplace transform basically does exist for when it does exist. And so if I know that the Laplace transform of 1 is equal to 1 over s, then I can go the other way and say the Laplace inverse or the inverse Laplace transform of 1 over s equals 1. So now I have this whole other chart I could draw. So where instead of having this right here, I can say f of s, and then over here, Laplace inverse of big F of s. And that'll be now back a function of t. So just by reading the table backwards, I have a whole table of inverse Laplace transforms. So what functions can we take the inverse Laplace transforms of? Well, if we look at the right-hand side of our table, we see that we have things like 1 over s, or 1 over some linear factor of s minus a. We can do a constant over powers of s. We can do things with s squared, things that are over s squared, even if there's an s over s squared, and then powers of these linear factors. But really, it's just kind of these rational type functions that we know how to take the Laplace transform, the inverse Laplace transform of. We don't know how to take the inverse Laplace transform of something like sine or cosine. So you'll see all the exercises in this chapter are, take the inverse Laplace transform of something that looks like something that's on the right-hand side of this table. And the big trick we see in this chapter is using partial fractions to break some more complicated rational function. Remember, a rational function is a polynomial divided by another polynomial. And you take some complicated rational function and break it into things that look like the terms that are on the right-hand side of this table. And so we'll go through how we do that. We'll do one of the more complicated problems that should give you the gist of how we do that. So let's clear some space. I'm going to do section 7.4, number 26. And we are given this function big F of s. So now remember, we're living in the Laplace S universe right now. And this equals 7s cubed minus 2s squared minus 3s plus 6 divided by s cubed times s minus 2. So there are a few different cases for what you might have going on here. And they are covered in the book. And so you should read through all the examples in the book for tips about how you do all the homework problems. So there's a couple of things to look out for. The first is that you need to make sure that the power in the top is less than or equal to the power in the bottom. I think it has to be strictly less than, actually. So we have the highest order in the top is 3, and then in the bottom we have 4 powers of s. So we don't have to do any long division or anything like that. There is an example, well, there may or may not be an example in the book of where you have to do long division. But anyway, let's not worry about that at this point. So we know we don't have to worry about that. And then the second thing is you have to figure out what case you have in the denominator. So in this case, we have it's already factored for us, which is nice. And then we only have linear factors. Our two factors are s and s minus 2. But we also have that s factor repeated 3 times. And so whether or not you have linear or quadratic factors in the bottom and whether or not they're repeated tells you the different cases for how you break up you can break your fraction up into partial fractions. And again, that's definitely in the book. So in our case where we have repeated linear factors, we know that we can write this rational function, this big F of s, this way. We have, first we'll do our factor of s. So we have some constant a over s. Because it's repeated, we have to take an s squared, and then we have to do that again for the s cubed. Now, because it's a linear factor, we have a lower power, just these constant factors, a, b, and c up in the top. And then our last one is going to be a d, again, a constant because it's a linear factor, and we have s minus 2. Okay. So now we just have to figure out what a, b, c, and d all have to equal. So because we've got these two equal to each other, we're going to multiply by s cubed s minus 2 on both sides, and that will give us that. On the left-hand side, we'll be just left with the top 7s cubed minus 2s squared minus 3s plus 6. And on the right-hand side, when we multiply everything by s cubed times s minus 2, we will be left with a times s squared s minus 2 plus b times s minus 2 plus c times s minus 2 plus, let's make a smidge more room here. Whoopsie. Plus d times s cubed. Okay, so now I'm going to sort of do this 2 different ways. And I mean, you guys have all taken high school algebra and you know how to figure this out, but I'll give you sort of an example of how the 2 approaches you can use. So first okay, this equality is going to hold for all values of s. And if we plug in certain values of s, then it will not have any variables anymore, and we'll just have, except for our a, b, c, and d, but we'll get rid of s if we plug something in for it, and then we'll sort of narrow down our search space. So let's try plugging in s equals, and what should we plug in s equals? Well, I'm going to plug things in that are going to kill off some of the terms over here. So if I plug in s equals 0, that will give me, on the left-hand side, I'll just get 6. And on the right-hand side, I will get negative 2c. And so that gives me that c equals negative 3. Well, that's nice. So that's one of my my letters that I need to solve for. So the other really obvious choice is going to be s equals 2, because now that'll kill off those terms right there. And if I plug in s equals 2, I already did this beforehand. On the left-hand side, I get 48. And on the right-hand side, it kills off the a term, it kills off the b term, it kills off the c term, and I'm left with 8d. And so that tells me that d equals 6. So now I only have two unknowns left. I have a and b left to solve. There aren't any more obvious choices to plug in for s, but I can plug in anything I want. And if I just do two different things, I'll get two equations that both have a and b from them, and then I should be able to solve them. It shouldn't be a big deal. I can plug in s equals 1, s equals -1. Those are pretty easy to calculate. But I'm not going to do that right now just because I want to take this opportunity to show you the other way that you could have approached this problem from the start. So let me take my C and D and simplify everything that's going on. And so up on the top, I still have my left-hand side is the same. So we get 7s cubed minus 2s squared minus 3s plus 6. And now let's write out the right-hand side as just like a regular old polynomial. Or first I'll expand it out and then I can try to simplify it. So I got as cubed minus 2as squared plus bs squared minus 2bs. Now I know that c equals -3, so I get a minus 3s plus 6, and d equals 6, so I get a plus 6s cubed. And I can simplify all this a little bit, and I get grouping all the s cubed terms together, so I get a plus 6 s cubed, all the s squared terms, plus b minus 2a s squared minus 2b plus 3s plus 6. Now let me rewrite my left-hand side over here. We have 7s cubed minus 2s squared minus 3s plus 6. So now we can just compare coefficients like we've done a bunch of times before in class. We basically get 4 equalities that come out from this. We have 7 equals a plus 6, -2 equals b minus 2a, -3 equals -2b plus 3, and 6 equals 6. So we'll solve these one by one. 7 equals a plus 6 gives us that a equals 1. -2 equals b minus 2a. A equals 1, so we can write this like b minus 2, and then that gives us that b equals 0. And let's go through the other ones just to make sure that everything is consistent. We get -3 equals -2b plus 3 if b equals 1, or b equals 0, then that gives us -3. That's good, and then just to check, we can write 6 equals 6, and we're good to go. So now that we have our A, B, C, and D, we can sort of fill all those in up here. So let's see, we have, we can rewrite this as A is 1, B is 0, C is -3, and D equals 6. So we now have a better way to rewrite our function, big F of S. And so let's do that on a clean slate. Okay, I'm gonna keep my work here for a second and then I'm gonna erase it. So let's remember what we're trying to do. We're trying to compute the Laplace inverse of big F of S. No, that was an ugly brace. And we can write that instead as the Laplace inverse of 1 over S plus the b term goes away as 0 minus 3 over S cubed plus 6 over S minus 2. Okay, and now that I've done that, I can get rid of this whole bunch of stuff that I did up there. Okay. Now, one property that we see in this chapter that I haven't talked about in the video, but I talked about in lecture a couple weeks ago, is that the inverse Laplace transform has the same linearity property that the regular Laplace transform has. And it's sort of obvious if you think about what that all means. But we're going to use that linearity property now. And that means that we can break up the sum and write the Laplace transform of the sum of things as the inverse Laplace transform, as the sum of the inverse Laplace transforms. So 1 over S minus 3 times the inverse Laplace of 1 over S cubed plus 6 times the inverse Laplace of 1 over S minus 2. And so we see now that all the things inside the curly braces are things that are on the right-hand side of our table of Laplace transforms. And so let's get that table back up. There it is. And remember, the way we were thinking about it is that we're going to think about this is our f of s over here, and then this over here is going to be our inverse Laplace of f, of big F. So our first term here, if we have 1 over s inside the curly braces, then our inverse Laplace is going to be 1. Sorry, there's a thing in front of my screen that I can't figure out how to get rid of. So I will write just 1 for the inverse Laplace of 1 over s, because 1 is the function whose Laplace transform is 1 over s. My s cubed, I can see that I'm going to have to use something like this, but that one is looking a little bit tricky to me right now. I'm going to hold off. I'm just going to write 1 minus 3 plus inverse of 1 over s cubed, and I'm going to save that for last. And then plus 6 times, now I've got a 1 over s minus 2, and that looks just like this one right here, 1 over s minus a. You can say a equals 2, and I know then that my inverse Laplace of 1 over s minus 2 is just going to be e to the 2t. Okay, so now let's go back to our green one. And let's get some, we'll go over here. And I want my table up here, so let's look at the Laplace inverse of 1 over s cubed. Okay. So what does this equal? That's supposed to be a question mark. So I don't have exactly what is shown over here on the right-hand side, because I have my sort of n should probably equal 2 so that we get n plus 1 power on the s, but I don't have that 2 factorial up in the top. So let's think about this. I know that the Laplace transform of t squared equals 2 factorial over s cubed, okay, which equals 2 over s cubed. So that means that I can put a 1/2 on both sides. 1/2 times the Laplace transform of t squared equals 1 over s cubed. And so that means I can bring the 1/2 inside the Laplace transform. Laplace transform of t squared over 2 equals 1 over s cubed. And that tells me if the Laplace transform of t squared over 2 equals 1 over s cubed, that means that the inverse Laplace transform of the right-hand side, 1 over s cubed, equals t squared over 2. Okay. So that I can put up there, and this is going to equal, I can erase those, get my black pen back, and I get t squared over 2. So that you probably don't, you may not have to write out all of the steps that I just did. You could sort of, whatever you need to do to make it make sense in your head. But anyway, that's what you do. So now we're going to take this fact over that the Laplace inverse of 1 over s cubed is t squared over 2. And let's head back over here. And keep writing. So now this equals, we've got 1 minus 3 times t squared over 2 plus 6 e to the 2t. And that's about it. We can simplify this a smidge if we want to, but we don't feel like it. And that's our final answer. So that's just sort of an example of how you compute some inverse Laplace transforms and go back to our T universe. So what we're going to see in the next section, which is our first new material since spring break, is how we use this to solve differential equations by starting off with a differential equation that lives in the T universe, moving it to the S universe, figuring out what the answer is in the S universe, and then doing the inverse Laplace on the answer that we got in the S universe, move it back to the T universe, and then we're done. So we'll see that in our next video.